Right, hopefully a quick one, circular motion. Let's start with this set of equations. These ones that I've written down are the equations you get given in the exam, so make sure you know what they mean. Now, this bit, angular velocity, what that's looking at is how much of an angle per second something's going round. So if we had a circle, if we had a clock, and we were looking at the hand going from the 12 down to the 3, that's gone 90 degrees in whatever time. So if it was the second hand, it would have gone 90 degrees in 15 seconds. So what we could do is we could call that a velocity of 90 divided by 15, which is 6 degrees per second. However, we don't use degrees when we're looking at angular velocity. We want it in radians per second. So you need to make sure, first thing in the specification is knowing what a radian is. Okay, now all you really need to know is that in one circle where we have 360 degrees, we've got 2 pi radians. Okay, so if we want to know what a radian is, our 1 radian is going to be 360 divided by 2 pi degrees. Okay, so if we've got 4 radians, we could work out how many degrees. So that's the first thing. Make sure you're clear on what a radian is. So angular velocity is measured in radians per second. Okay, and normally they just write radians second to the -1. Now, if we want to know about the actual linear velocity, V here stands for the linear velocity. So as we've got something going around a circle, at any point, its velocity is at a tangent to that circle. So we've got linear velocity there at a tangent to the circle. We could work out what that velocity is if we knew what the radius of the circle is and if we knew what the time period is. Now remember, the time period is measured in seconds and it's the time it takes to do 1 revolution. Okay, so time period T is the time it takes to do 1 revolution. Also remember, frequency F is how many revolutions per second. And those two are related. T is 1 over F and F is therefore 1 over T. So to find out our linear velocity, if we knew what the radius was and we knew what the time period was, well, the linear velocity would be 2 pi r, which is the distance that it goes, divided by t, the time it takes to go right round the circle once. Now you can see up here from our definition that omega is 2 pi over t, so we could, instead of writing 2 pi r over t, that's where this comes from. Now we've got 2 equations for acceleration, whether we want it in terms of linear velocity or angular velocity, and just using F is equal to ma, sorry, that should be an m, F equals ma, the force, it's just the mass multiplied by the acceleration. Now when we're looking at something going around in a circle, it's always the mass of whatever it is going round. So whether that's a stone being whirled in a circle, something like that, it's the mass of that we get. Now the force, the centripetal force, that is made up of whatever forces are present. So if we had an example of a bung being whirled in a circle on a string, the force would be made up of the tension in the string, and if the string was being whirled vertically, then a component of the weight might be forming part of the centripetal force. If we had it down at the bottom here, if it was in a vertical circle, the centripetal force would be formed out of the tension. The weight would be acting in the opposite direction. So your centripetal force would be T minus W. If we've got it at the top of the circle, then both T and W are acting down, so the centripetal force is T plus W. So always consider what forces are acting. Now, you need to be able to explain about the experiment whirling round a bung. What that experiment uses is our equation F equals mv squared over r. Now, we use a set of masses to provide m. So what you've got there is you hang on the end of your string a set of masses, and you calculate the force using F is equal to mg. So that's to find that force. Then you have the string going through a tube, you're whirling it around, and you've got to keep the radius at a constant distance, or it depends what you want to measure. You can either, usually what we would have done would be to keep the radius the same, about 20 centimetres, and we'd do that by making a mark on the string using a felt tip. Now that's where you're going to get your biggest source of error from, because it's very difficult to keep that going at a constant radius. We also get a big source of error because of the friction as the string hits the tube that we're rotating it in. What you do then is you vary F, you measure the time, and that gives you the ability to work out V squared, and then you draw a graph of F against V squared. The gradient of that graph would be equal to m over r. Now we know r, so it would be a way to work out what the mass of that bung would be. You could do it in other ways where you could be trying to work something else out, but that's the usual way that they show it. Now, circular motion, really related to gravitational fields. I might put up a bit about that later on.